Hello, everyone. I hope everyone is doing well. I'll be presenting Unveiling Rift, Advanced Pattern Matching for Rust Libraries. And I guess the title already says a little bit about what I'll be talking now. But before I talk about myself and the outline, I might want to just share a situation many of us might have or already had if you do reverse engineering. So you're working maybe in a SOC or you're a reverse engineer and you have an Intel team you work with and they come to you and say, hey, we had this incident, here is this binary, can you maybe reverse engineer it? We really need to go deep into it. We need to understand the C2 channel, the capabilities, get the config out of it. And you'll open it in your favorite disassembler. It might be IDA, Binary Ninja. I don't know, when I reverse, I go for the quick wins first. So I look at the strings maybe, and you see something like .rs at the end, Rust C, some commit hash, and the decompiled output just looks crazy crap. And at some point, you're looking at a Rust binary, right? And this is usually my reaction when I get something like this, and this is what motivated me to work on this problem. And a little bit about myself. So I'm a reverse engineer at Microsoft Mystic, Mirage team, member of the Malware Intelligence Research and Analysis Global Expert team, Mirage. I focus on reverse engineering nation-state malware or malware used by nation-state threat actors. And I'm also the maintainer of malwareandstuff.com. So I write something about reverse engineering every now and then there. So what I'll be covering today is, in general, I'll talk about a tool called Rift, which we'll be open sourcing. And I first cover some basics, so talk about Rust, what challenges you have when you do reverse engineering Rust, something a little bit of the developer's perspective, so what tools a Rust developer usually works with. So we have some foundational knowledge around it. And then I'll introduce Rift. We use it on some real-world malware to show how it looks like, and then I finish off with key takeaways and some roadmap ahead, like what's being planned with Rift. So, what is Rust? Essentially, as you all know, it's a programming language. It enhances type safety, memory safety, concurrency checks, and overall, for a language, it's a great thing, right? But for us reverse engineers, it's really painful to deal with because you get lots of boilerplate code in there. There is like an abstraction layer that is being added, and that means that you first have to filter away this abstraction layer. Additionally, the industry standard compilers fail currently to decompile it properly. I think some of the reasons are that they do not support some of the features these modern languages have, like multiple return values, for example. And the next thing and the problem Rift focuses on is that they are statically linked, or the libraries are statically embedded into the binary. And that means, as an RE, you first have to distinguish between the library code and the author's code. So to illustrate this, we conducted a little experiment, right? We wrote 2 PE files. On the left side, you can see it written in C++. On the right side, in Rust. They both do essentially the same. They download a file from a URL that you input through the command line. The file is being saved as sample_data.txt, and that's it. And the left PE file was linked dynamically. So, in Windows, we'll usually deal with dynamically linked PE files. And for the Rust compiler, we just used cargo build mode with release flags, so no debugging symbols embedded. Then what we did a small function count, like how many functions you get in each of those binaries. On the left side, you can see it for the C++ program. You had 80 functions, so we loaded into IDA. We also distinguish between annotated and not annotated. Annotated means through whatever means IDA was able to flag it as a specific function from a library through flirt signatures, for example. Not annotated functions with a sub prefix at the beginning. So for the C++ program, we are at 80 functions. For the Rust program, we are almost at like 10,000 functions. And I don't know, I can't even see how many were annotated here, not many. So as a reverse engineer, you first have to deal with all of that not annotated code or try to really filter as much away to get to the malware author's logic, right? So with that, I'll speak a little bit about Rust itself. I'll speak first about it from component level, what tools you usually use if you write Rust. So you have usually 3 components and 2 endpoints. You have RustUp, which is the update manager, which updates and manages Cargo and the Rust compiler versions. rustc as the Rust compiler, and Cargo as the package manager. So if you're writing a program and you want to add a dependency, you say Cargo init project, and then you can add, for example, add request, which is a library for HTTP, HTTPS functionality. Luckily, the cargos, like the packages, are all uploaded on crates.io, which is a website where everybody puts their dependencies on. It's like a database. And the Rust compilers, you usually also don't have to compile them by yourself, because the team behind the Rust language, they have an HWS bucket, which is static rustlang.org, and they have pre-compiled Rust compilers already uploaded. So you can just say, I want to use rustc 1.65, for example, and you just download for the specific architecture and operating system you want it for. And this is on the component level. On the file system level, if you're on Windows and you're writing Rust, usually 2 paths are of interest. The first is that upper one with RustUp in it. And this is where RustUp manages all of the Rust compiler versions. And the cargo path at the bottom is where your project is usually at. And essentially, you have a couple of configuration files in that cargo project, like config.toml or cargo.toml, and all these config files are there to configure your project as you like. So which Rust compiler you want to use, which dependencies should be downloaded, and also like what target triples, so for which architecture and operating system you want to compile it. We need to talk about 2 more definitions, so a comp triple or target triple, because Rust is platform and operating system independent. Often you see strings like this if you look in the folder. Essentially, that's an identifier for which Rust version and for which architecture and operating system this precompiled binary is essentially here for. So you see rustc, then a version, x86, x86, 64, and PC Windows, so personal computer Windows, MSVC. The second thing, what we have to talk about are rlib files. So, rlib files, sorry. So if you have your precompiled dependencies and your compiler, it's when they are being compiled, it's not that they are in DLLs or something like this. They are stored in a format called COF files or object files. It's like an intermediate format. And when the binary is being, like the binary output is being compiled, right, these COF files and object files are being linked into your final Rust binary. And these object files or COF files are stored in something called rlib. So if you open this folder, you will see this very often, which is an RK format specific for Rust. And if you see me here opening libwindows_sys, what you will find here is that one.txt and lib.rmeta, and then in the final file here is that O file where the essential executable code is in there. So that's for the basics. I'll start talking about Rift now. And Rift is essentially an open source tool that should assist us in library recognition for library code in Rust binaries. It currently consists of 2 IDA Pro plugins and 1 Python program. So it can run in 2 modes, which I'll go deeper later, which is batch binary diffing and through flirt signature generation. The 3 components are Rift Static Analyzer, which is to extract static information from the binary. Then Rift Generator, which generates the diffing and flirt signatures. And Rift Diff Applier, as when we do the batch binary diffing, We need to consume this somehow, and fluid signature consuming is easy, at least for IDA. But for the diffing, we needed a way to visualize this, and this final plugin is there to consume all this information. So with this, I'll first talk about the static analyzer. So as I said, it extracts static information from the binary. And what some of these information you can get out is, for example, the different dependencies. So in the screenshot here, you can see base64 0.21.2. So this is, I think, from a ransomware called Ralord where they put this out, or some backdoor. And we can assume if we find the string there, okay, the threat actor very likely, or the malware author very likely, use base64 with this specific version in the binary. So that's the first indicator we get out. The second thing what we find is like this huge commit hash here. And essentially, as I've shown before with the components, Rust-C is the Rust compiler. And this commit hash you have here is the version or the commit hash of the Rust compiler that was used to compile the malware or the binary output. So if we reiterate, we have now the dependencies, a list of dependencies, and we have the commit hash, right? Now, it would be great if we come from the commit hash to the Rust version, and luckily the Rust team on the HWS bucket, they essentially upload a TOML file for each precompiled Rust compiler. And this TOML file contains also the version of the Rust compiler. So by getting this commit hash and parsing all of the HWS bucket, pulling all of those TOML files, you can build a database that maps from git commit hash to the corresponding Rust compiler version. So now we have the Rust compiler, we have the version, we have the dependencies. The next step would be to try to build or recompile all of these dependencies so that we can do pattern matching or fluid signatures on them. And this is essentially what this Rift generator does. It's a wrapper around a set of tools that already exist. For compilation, currently, it wraps around RustSub and Cargo. And it goes through the process of initiating a project, adding dependencies, configuring all these configs. Then it also needs to depend on the Rift static analyzer input, which is fed in. The fluid signature generation wraps around Hexray, Sigmake, and PCF. So if you've ever done fluid signatures, those tools are there to assist you in building these. And the binary diffing wraps around Diaphora and IDA, so IDA Pro text interface binary. So IDA, the way you usually use it is you have your fancy GUI, you open it up, and you have your GUI on IDA Pro. But it also has a text interface binary that's faster if you run it in batch mode or because it doesn't essentially spawn that GUI. Diaphora is a great binary diffing tool. It's a plugin. So if you ever didn't heard about it, it's awesome. I really recommend you to trying it out, and I'm thankful for the guy to open source it. To illustrate the whole process of how this Rift generator works, it goes through 4 phases. So we have compilation, the project is initialized, we configure the project, the crates are being downloaded and compiled. Second phase, we go through collection. As I've mentioned before, in these paths, we find these rlib files, so we have to get the conf files out first. We do that, we store them temporarily, and then we either go through the fluid signature generation or the auto diffing. For the fluid signature generation, we generate first pad files with PCF, and then for the compiler itself, because if you open up these paths, you see that for dependencies and for the compiler, you will have multiple conf files. That means we actually compress them or put them together, and for each dependency and each Rust compiler, you will have one SIG file, one fluid signature, so you don't have like 100 of them for one project. And for the final part, which is that auto diffing part, I think it's better explained in the next slides. As I've mentioned, we use IDAT and diaphora for the batch binary diffing. What we do, or if you ever use diaphora, diaphora, you run it on an IDB file, and it generates an SQLite file. And this SQLite file contains critical information that diaphora needs to do the diffing. And essentially, we use IDAT to first go to IDBs, and then we use diaphora to go from IDBs to SQLites. Then we have like our target malware SQLite file, and for each COF file that's of interest, we have also our SQLite files. This is in the first step. In the second step, we do a one-to-n diff. So n being the COF files, the libraries, and the Rust compiler COF files, and 1 being the target malware. And what we get is then a set of n SQLite files that contain the diff results, basically, right? So lots of SQLite files today. And what we do at the end is we compress everything together into one big JSON file. So what we have by this end is like a database of like a lookup database where we see, okay, for this function, we have maybe 7 hits, and the top 5 hits have like 0.85 similarity, right? So it's like a lookup database where the flirt signature is essentially failed. So with that, talked a lot about how it works. I now speak about or apply it on some real-world malware. So I've mentioned the 3 tools before, or the 2 IDA Pro plugins, and this Rift generator. We essentially go through the same steps or similar steps again. We first extract the static information, which is through the IDA Pro plugin. Now, I was a front-end developer for 6 months, and yeah, you'll see why only for 6 months. So this is what you get for now. But it does the job. You essentially put in where you want to save your data in. This is where the data is being extracted in. You can print, which is just for cross-checking that you get everything out. And what you get out of this is essentially this JSON file. And this contains the git commit hash, the target triple, and the architecture. 686.64 and PC Windows here, or Windows, and the crates or the dependencies. So which dependencies are essentially we were able to extract or find in the malware we are analyzing. Now, in the next step, what we are going to do is we load it into Rift. This is how the command line looks like. You essentially input your config path. This is where the config file takes the path to all those tools. So where PCF is at, where SIGMake is at, where diaphora is at, and IDAT. And then you can decide whether you want to do the binary diffing or the flirt signatures. In this case, sorry, I forgot to mention, we are doing this on Ralord. So if you never heard about Ralord, it's a ransomware that was released, or it came up, I think, end of last year or beginning of this year, and it was a great use case for the flirt signature case here because it's not too big, and the functionality is it's still simple. It's encryptor, so it just really ransoms your data, encrypts your data. So this is being applied on Ralord here, and after generating the flirt signatures, this is what you get out of it. The set of flirt signatures. So for each dependency, you have your corresponding flirt signature, and for the Rust compiler, 81.84.1 here. And to show you some of the results we had on Ralord, on the left side, you can see parts of the main function, the decompiled main function. On the right side is like a window where we have all of those subroutines that were not identified. And this was after applying it. So you can see on the right side that at least that Rust-C demangle library was well detected. Many of the stuff you would not want to look at, like this fill bytes or down there unwrapping failed, lots of that stuff which you actually want to extract away when you start analyzing malware. is properly detected. So this is for the fluid signature approach. The second approach, which I mentioned and I'll talk about, is the binary diffing one. So here we do it on Spica. So Spica is a Rust backdoor that was by the Google team attributed to Starblizzard. So I just know Starblizzard, the term now. It's a Russian nation state actor, and it's a full-fledged backdoor that can extract various cookies or information stealing, C2 capabilities. So the number of features are pretty far greater than on the simple ransomware. In this case, we go through the same steps again. So we extract the static information, we feed it into the Rift generator, which is again this command line here, except that in this case, we don't just do the fluid signatures, we also do the binary diffing. And the fluid signatures are applied too, but we realize maybe the fluid signatures didn't really well or worked as we thought it would work. And there are like lots of libraries that were not properly detected. So we use the binary diffing approach. After you run the Rift generator, as I've mentioned before, you're up with this database, this results.json file, which merges all of the SQLite files. And you feed it into the second GUI here. You basically say import JSON file. It currently has 3 features or 2 features. So when the files are in the COF file, the names are mangled. So mangling is like an encoding that the linker uses. And you need to, we give an option to demangle it, but we use an open source library for it, which is Rust C demangler. And what you can also do is you say, do the auto renaming. So you can say the ratio here is the minimum similarity that you allow for functions to be displayed or to be auto renamed. So you can say only rename functions with a similarity of 0.97%, and it will ignore all of them and will always take the best fit, basically. Or you can say select ratio here is if you want to use it interactively. You can select the ratio here again and will just load the ones that have not less than your ratio you select, the similarity ratio. So how does this look like once you click OK here? Essentially, you'll have 2 windows at the end, or one is already there. The second one is generated through Rift. This is at the bottom right and top left. So on the top left, you have your usual window on IDA, so your function window. Some of the fluid signatures were applied correctly, as you can see here, but some of them weren't. And in the bottom right, we give you like some interactive window where the functions are being displayed. What you can essentially do then is we give an option to do either with Control X, which is the default shortcut, or you right-click on the function, scroll down, select Rift, display top matching functions. And this window will populate which functions had the best matching results here. So in this case, we select one function from above where the fluid signatures failed, and we see that we have a 0.97 similarity score from some studsys Windows FS stat function. So this has been very helpful when we had to do a deep dive, and the fluid signatures didn't really work as we expect they would be. This has been helpful to still strip away lots of library code. So with that, to some key takeaways. So Rift will be open sourced and announced with a blog article. So it will essentially be announced once I click on the button, and I hope that button works. The plugins are currently limited to IDA Pro, and Rift Generator was tested on Windows. There is like motivation to do this for the other disassemblers too. I'll speak about this in the roadmap ahead. In the next slide, and both approaches have their strengths and weaknesses. So the fluid signature approach is very reliable, so the RODs you get are pretty reliable. It's accurate and very strict. they are faster to generate as you don't go through that binary diffing approach, but they are not well applicable if the static information fails for some point, like I don't know, you don't find the corresponding Rust compiler, it was packed with VM protect or whatever. For the binary diffing approach, it's more prone to false positives, as you do, like you go with similarity and they're not as strict as the flirt signatures. It needs manual validation, and it currently takes lots of time to do this binary diffing because we go through IDAT and then we go through diaphora. And essentially you maybe have like 30 COF files you need to do this on. And this needs some improvement, but this is also on the roadmap. But this binary diffing approach can also help a lot when you don't have the static information, right? Maybe you don't know the exact Rust compiler version, but you know maybe a time frame, and maybe you want to still try to binary diff with an older, or you kind of have an idea what version it might be, then this approach can still strip away from some library code for you if you're doing a deep dive or really going deeper into our malware family. So for the roadmap, like I said, so we are expecting to support other architectures too, so I'm working on this. Currently it's for Windows or tested on Windows. The binary diffing approach is, like I said, currently very time-consuming. The support for other disassemblers is planned, so this depends a lot on the adoption trend here. We are experimenting a little bit with AI, but the stuff that more I'm interested in is trying to really clean away the library code from it and build like a ground truth for like training something on malicious code on Rust. And final point is, this is open source, like contributions are very much encouraged. So please try it out. If something doesn't work, let me know, do an issue. So this is for me like a first step going forward with trying to make Rust less painful to reverse engineer. So hopefully maybe next year I'll come back and have that second slide with the guy crying there. Maybe I have him smiling at the end, hopefully. Yeah, that's for the roadmap. Finally, some special thanks to Aled Mason, Eric Merritt, Ramin Nafizi, and Stephen Barnes. They've helped me a lot with setting this up and also with the blog article and testing stuff for me. So thanks for them. And yeah, that's it. Thank you for listening and coming. Are there any questions? Yes. Yeah.
Do you figure out which crates are being used based on the string data in the binary? Do you have, like, if the actor scrubs those from the binary, are you basically screwed? Or do you know if there's other ways to figure that out?
Yeah, so if the strings are screwed, you would have, with flirt signatures, you'll probably be not with the right approach. You can do the binary diffing approach. Another way you can basically try to do is to have flirt signatures for all kinds of library versions. That's the way you could go. But I would say not screwed, but you need to invest more time, right?
Hi, thanks for the talk. You mentioned it's open source, but I didn't see the URL.
Sorry?
Maybe I missed in the beginning, like where you can find this project.
Oh, where you can find this project? It's on GitHub. So
yeah, a specific project name.
It's Rift. So if you check GitHub, Microsoft Rift.
So it's under Microsoft.
Exactly, it's on the Microsoft organization repo.
Yeah, and another question. In IDA 9.1, in IDA feeds, we added the option to generate Rust signatures directly from the binary. Have you tried it?
Yeah, I've tried it. It works also well, but it doesn't do it for the crates. So yeah, for the Rust compiler, it worked well, but we didn't have the crates.
Yeah. Okay, thank you.
Yes?
Thank you. Thanks for the great talk. Have you done any investigations into the accuracy of this, particularly around like false positives? What if you rename a function that is in fact incorrect?
Again, sorry.
Have you investigated kind of any false positive rates around detection of functions? Do you know the accuracy of how well your approach works?
So I had a couple of samples I've tried this on, right? Like with manual, but there was no large scale work on this yet. I figured that with the samples I worked with and the samples I reverse engineered, the fluid signature approach worked quite well. So I did not spot any big false positives where I say, okay, like this is awful. The binary diffing approach, I would probably not go with the enable auto renaming. So it was more for an interactive approach. Or you say you want to write a detection and you know you have a function and you really want to know is this going to be a library or not? This was where it was very helpful. But for like large scale testing, not yet.
Yeah.
But if you're trying it and you do it, please let me know. This is why it's open source also for, as this is like a big problem. And I think we all agree Rust is incredibly painful to reverse engineer. So there was another?
Yeah, sorry, I have a question. Maybe good talk, by the way, thank you. Maybe I missed it, but have you found if there's any obvious way to figure out which features are enabled for a given crate?
Yeah, that's on the next step I have to look at.
Okay.
So overall the Rust compiler flags is, I think, an important thing to look at as what's possible there. I didn't look at this yet. Okay, I don't spot any more questions. Okay, awesome. Thanks a lot.